Hello, everybody. We're going to get started at roughly on time this time instead of postponing it because we have to. There's another talk in here at 2. My name is Jeremy Manson, and welcome to the latest in our series of programming languages talks. I like to take a minute before every talk to try to inspire people a little bit to give a talk of their own. So if you've got something that you think might make a good talk, and I see several people in this audience who I know would be great speakers, then please come up to me either after the talk or email me later and tell me that you'd like to give a talk and we can set something up. All right, so I've actually always been tempted to give an introduction by saying this man needs no introduction and then just walk away. And I think it would be appropriate in this case. But I'm going to give an introduction anyway. Our speaker for today is Rob Pike, who, among his other accomplishments, is responsible for things like UTF-8 and Plan 9 for Bell Labs, and one of the first bitmap systems for the Unix operating system. And he's here today to talk about a programming language that he developed while I guess he was working at Bell Labs, called Newsqueak, which has some interesting mechanisms for concurrency and message passing. So without further ado, here he is.
Thank you. Of course, I could say I need no introduction and walk away too, but I won't. I'm going to talk about some work I did almost 20 years ago now. So a lot of this is going to be unfamiliar to you and unfamiliar to me because I've had to page it all back in. But there's some interesting ideas in here, and I think a lot of them have been forgotten, and I think really deserve to be thought about. And they all stem from this notion that we live in a concurrent world, but we use sequential computers to write programs. And there's a really profound mismatch between those two models. And there's two obvious ways you can deal with this mismatch. One is to somehow make the world look synchronous and sequential, which is pretty much the way most things are done now. Or you can try to make your software concurrent. And this talk is about number 2. Now, I want to start by saying what this is not about, because I think it's a common misunderstanding about concurrency. A lot of books, including some that are very highly regarded that I won't name, start by telling you that concurrency is one of these awful things that you just have to deal with. There's all these parallel devices and parallel interactions, and it's awful, and computers have multiprocessors, and it's horrible, hard. So you've got to learn it and think about it as a solution to a nasty, gnarly problem. I think that's a really unfortunate way to think about it because concurrency has nothing to do with parallelism. They're actually separable ideas, and that's important. And moreover, there are concurrent programs that have no intrinsic parallelism that are actually much cleaner and more beautiful than the sequential versions of the same thing. I'm going to show you a few of them later. This talk is not about how to make parallel computers run faster. This talk is about how to make programmers more effective by thinking about some problems with concurrent models. On the other hand, once you've got that in your head, if parallelism comes along, you've got a great tool. This all comes from the notion of what a state of a program is. And the way computers work is, you get a program counter and a stack. And the state of your program, ignoring the sort of memory that's underneath it, can be represented by a stack and a PC. And you see that when you go into the debugger and ask what just happened, you get a stack trace back, and you see I'm here, and here's how I got there. And you can consider concurrent program as just having lots of those things together. So the state is just a linear agglomeration of a set of PCs and stacks. And the thing is that the composition of those PCs and stacks can become exponentially more powerful in what it can do. But conceptually, it's a very simple, almost sort of linear kind of thing. Now, clearly, there's a huge layer of bullshit I just laid down, but bear with me. So how are we going to make a concurrent program with a set of PCs and stacks and actually do something with it? So the model is to think about software as a set of things, interacting, independently executing processes. And Tony Hoare, bless his Oxonian heart, wrote a paper in 1978 called Communicating Sequential Processes, which really set the ground for all of this work. And all the stuff I'm going to be talking about is derived from that, but takes it in quite a bit further. One of the things to point out is that we're missing a lot of the words people expect you to talk about when you're talking about concurrency. I'm not going to use phrases like threads, shared memory, locks, semaphores, all those kinds of things. I'm pretty much taking Andrew Birrell's model. He popularized a model for thinking about concurrency, and I'm just ignoring it. Not because it's not correct and not powerful or not good, but because it's too low level for the way I want to think about programming. I want to work at a higher level and not have to concern myself with these low-level concepts. So the Birrell model is great for writing operating systems, not so great when you want to just write an interesting program like some of the ones I'm going to show you. Very briefly, there's a fairly rich history in this stuff, and this is just my sort of slice of it. I'm leaving out a lot of work in things like concurrent ML and Ackermann and stuff like that. But in 1978, Hoare wrote this absolutely brilliant paper on CSP, which introduced the concept of communicating sequential processes. But it missed out something important that was discovered by a bunch of people later, including Hoare himself, which was this notion of a channel, which I'll talk about quite a bit. Luca Cardelli and I, in 1985, wrote a paper about a little very, very silly toy language called Squeak, which used concurrency to express graphical interactive interfaces much more concisely. And it wasn't a real system, you wouldn't really want to use it, but it pointed out a lot of the issues that come up when you try to write software for a concurrent world. And it scratched an itch I had and got me thinking about some stuff. So about 1988, I did this language called Newsqueak, which was a real language you could actually write programs in, which was not true for Squeak. It's a full language. You can write real programs in it. It's interpreted. It's not particularly fast, but it's fast enough for what I want to do with it. And it's kind of odd because I don't know if this has ever been done before, but I actually wrote a programming language in order to write a single program. And the program I wanted to write was a window system. And I'll talk a little bit about that later. But I had users for Newsqueak who went off and did all kinds of interesting things, which I'm going to talk quite a bit about later. And it also inspired a few other languages. Phil Winterbottom in 1995 may be offended by me saying this, but I think what he did was basically build a compiled Newsqueak, which we used as a systems language at Bell Labs for a few years to build a lot of interesting tools. In fact, for a few years, essentially all the big systems we built at the labs were written in this concurrent language, which was C-like but had full concurrency and message passing. And then a year or two later, Phil Winterbottom, Sean Dorrit, and I did a language called Limbo, which is still a product that's sold by a company called Vita Nova as part of an Inferno project. And it's very much like Newsqueak. So essentially, if you understand Newsqueak programs, you can understand Limbo programs. But Newsqueak is JITted. Newsqueak is interpreted, but Limbo actually has a JIT, and it's reasonably efficient. So the overview of this talk, I'm going to talk a little about Newsqueak, but I'm not going to really concentrate on the language as such because there's a lot of things in the language we don't need to talk about. So I'm missing all kinds of features of the language. I just want to present enough of it that you can understand the examples. And then I'm going to talk about what processes are, or at least how you think about them in Newsqueak, what channels are, how you write programs this way. And then the really interesting part is towards the end where we start building interfaces with these ideas and eventually maybe build some system software on top of that stuff. So an overview of Newsqueak. How many people in this room have used Sawzall or at least are moderately familiar with it? OK, if you've used Sawzall, the syntax can be very familiar. It's not the same, but it's very familiar. That's not a coincidence. But Newsqueak is a much richer language. It has a much more interesting semantics. And of course, this whole concurrency and communication stuff is absent from Sawzall, but is the whole point of Newsqueak. So to a very rough approximation, it looks like C with Pascal declarations. But it's not C-like because it's got functions as lambdas. So you can actually have expressions as functions and do all kinds of interesting things with them. It's obviously got process management software built into it. And these channel things, which are, when I was doing it, seemed to be the good idea, and I still think probably are first-class citizens. And there's control structures that I'll talk about that let you do things with channels in interesting ways. And then perhaps the single most radical thing in Newsqueak, although it doesn't come up much in the talk, but it's relevant, is this notion that every memory cell is value semantics. That is, everything is a value. There are no references anywhere in the language. Sawzall has the same property. People, when they start using Sawzall, are still sort of don't believe that that could be true, but it is true. And it has implications for how you think about concurrency and shared memory and stuff like that, which are important, but I'm going to just sort of gloss over because it's not that interesting to the model I want to talk about. But it's important to the way the language actually works. So here's some really stupid little snippets of code just to give you a flavor of what it looks like. Not so these do anything interesting, but so when you see more interesting examples, you'll understand them. So here's a declaration with a type and initialization value in the variables. That says declare hello. It has this type, and it's got this value when it's created. And for these next two slides, I put the keywords in blues just to make it a little easier to figure out what the syntax looks like. So this odd little thing here is actually a declaration. It says declare a variable called I, whose type and value is this expression. So it creates an integer variable and gives it initial value of 47. This weird-looking thing here is, think of muck as the new operator. Here's the type of the thing, and it's an array of arrays. It's got an initialized value, and again, this is just a value with a type that initializes and creates a variable called b. And muck gets used in creating things like channels, which is why I had to show it to you here. And then just to show you it's not all that weird, here's a loop. It looks very much like a C loop in a lot of ways. There's a built-in print statement, which is not very interesting, but you need something for this. So these should be pretty easy to understand. Here's Ackermann's function, just so you see what a function looks like. And it's starting to look a little weirder now. There's a keyword rec, which means recursive, which allows you to define a block in which the variables can refer to one another. So if you're going to define a recursive function, you have to put a rec keyword on the declaration. It's just an accident of the grammar. It's not very interesting. But it lets you normalize some of the definitions of recursive things without forward declarations, which is kind of nice. This keyword prog, think of that as lambda. And become, think of that as being like return, but it has very different properties, which I'll talk about. It's important. So anyway, here's how you write act. If you change become to return and prog to function, you can read it as a regular old Ackermann's function definition. And of course, calling it looks the same as always. So these function things, they're called lambdas, but lambda has too many characters in it, so we made it prog. We like short keywords. So here's a prog value, which is an integer valued function. That's the return type. And it just returns the sum of A and B, its arguments. So that's actually a value in this language. You can pass it around as a value. And once you have one of these values, there are 4 things you can do with it. You can treat it like a value, just assign it. You can call it, because it's a function. You can replace yourself with this execution, which is something I'll talk about. And you can also, obviously very important in this model, start a process running it. Let's go through those. So here's our value buried in here now, and I've turned it into an initialized declaration. So this is how you define a function called sum that has that lambda as its value. Okay? And then here's another one, difference, which is the same thing. Notice this become here. We're going to come back to that. But this should be fairly obvious what's going on. And then this is not interesting in any way, but you could say sum equals difference. The functions are just functions. It's very, very simple stuff. So you've got lambdas. You can assign them. You can treat them just like lambdas. Of course, you can call a function any way you normally would. So here's our sum function again. And we can initialize the value a to be the result of calculating sum of 24 and 23. And this is exactly the same result, but done without actually creating this sum as a function. We just use the lambda, and then the call is done by just invoking parenthesized parameters right after the lambda. This, again, should be very familiar to anybody who's programmed in any kind of lambda world. So the reason I'm going through this is we're going to use these things a lot, and I want to make sure you're comfortable with them. So is everybody comfortable with the whole simple lambda thing here? OK. Now, this is we're getting a little weird here. There's no return keyword in Newsqueak, because although you can do a return operation with this become word, the become keyword represents a somewhat richer idea of what execution means. So the notion is that for any time when you're doing a calculation, you can replace the calculation you're doing by saying become with another expression whose value is the same type as the type you're already executing for. So that's a funny way of saying you can return that value. So here's a simple expression. Here's the sum guy with that become in it. So it says when you evaluate this expression prog, you do it by becoming the expression a plus b. Now, that just means return, except here's a slightly more interesting example. Here's a difference function, which is defined as the become of sum of a and minus b. And the point about this become here is that it truly is a become. It replaces everything about the calculation, including the stack frame. So although it's a recursive function, it doesn't grow the stack. And the implementation of Newsqueak actually worked hard to make sure it kept the stack as small as possible. And the reason was, I was thinking about interacting processes and mutual recursion and stuff with things actually pinging back and forth between evaluators of state machines without having to grow the stack. And I'm not going to show you much of that today, but it gets used a lot in one of the examples that I'm going to talk about, but not show you the code for. There was a question in the back?
Yeah, so you can't use become, you can't say become, you can't say plus become, a plus
No, become is a keyword that replaces the calculation you're on. It's isomorphic to return in the way you can't say plus return. You can just say return some expression. You can say become, it has to be an expression, a full expression. And there's some stuff in denotational semantics. If you like that flavor, you can identify what's going on here. But anyway, you won't lose any understanding if you just think of it as a return statement, but it actually is a little more powerful in the implementation sense, if not in the computational sense. Finally, the last thing you can do with a prog is invoke it as a process and set it running on its way. And to do that, just to be perverse, the begin keyword, I borrowed from Algol, but it means something completely different. What this means is not begin some block, but invoke this prog as a function, but start it on its way and don't wait for it to finish. I don't care how long it takes, just let me go. So after executing this begin, the next statement, whatever it is, there isn't one here, would begin executing immediately. So it's like fork or spawn or clone or any of those things, but defined as a fully typed function invocation. And if the function returns a value, the value is discarded. So you can, in fact, say become sum here, even though sum is a typed function. The value is just thrown away at the end, but it's not very interesting. So here's a slightly more typical kind of thing. Here's a prog that loops and does some complicated calculation. In this case, just prints a bunch of numbers. But here we are invoking it dynamically. So we're just launching a process and laying the whole thing out at once. We say begin, we write the spec for the program we're going to run, and we give it its parameters, and off it goes. And you see that kind of pattern quite a bit. But of course, there's something missing from this model, which is we don't know when it finishes. And to do that, we need some way of having the begun prog informing us that it's done something useful or there's a value to be recovered or whatever. Also, there's no join. It's just not in the language. The concept instead is you communicate to find out what's going on. So let's talk about that. So in the original CSP that Hoare did, there's a book he did later that has this stuff. In the original CSP, it did not have the notion of a channel. You communicate with a process. You actually wrote out a process and you talk to it. And one way to think about it is that it's the difference between doing I/O to a file versus doing I/O to a file descriptor. A channel is much more of a file descriptor than a file. It's a handle, and you can use it to communicate. A channel, which is introduced by the keyword chan in Newsqueak, is an unbuffered synchronous communication port. Unbuffered means that if you write to it, you have to have a place to put it. If there isn't a place, if the channel's got a value in it, you block. It's synchronous in the sense that when you write to it, you can't return from the write until someone has read the value out again. So not only does it communicate, it also synchronizes, which is very important. And it's fully typed. You can have any value you want inside a channel, including a prog, an int, even another channel, which gets used more than you'd think. It's half duplex, which is an interesting wrinkle. Although it's fully typed, there's no endedness to it. So once you have a channel, you can read or write or send and receive on either guy. It's arguably a criticism. It might be better to make the channels have a defined direction, but they don't. Again, that's sort of CSP. And there's these operator. There's actually one operator, which is the same operator, depending how you use it, is a send and a receive. And it looks like this. So here we are declaring a channel. So this is an uninitialized channel, and then we can assign it by doing this muck thing, which is like new, to create a new one. You could, of course, also say C : equals muck of chan event, which is the more typical usage. And there's this operator, which is the left-facing arrow, which is the communication operator. And the way you use it is if you put it to the right of the channel, it's a send. If you put it to the left of the channel, it's a receive. Now, there's a mnemonic that makes it easy to think about it. If the arrow points into the variable, then you're sending. If the arrow points out of the variable, you're receiving. It's pretty simple. And it reduced the number of funny tokens I had introduced. So in order to make things sort of regular, I made send actually look like an assignment. So that this is like you're assigning 23 to the channel. And this is perfectly fine notation. In practice, people tend to write it like this, so that the operator, this is really two operators in the language, but they glom into one. It looks like an assignment, send assignment. And the point about this thing is that you can have this way of communicating really simply with a channel. And the semantics are just taken straight out of CSP, which means when you're going to send on a channel, there has to be a receiver before the send will complete. When you're receiving from a channel, there has to be a value available in the channel, and that means there has to be a sender waiting for you, because it's synchronous that the sender won't have left the value behind. He'll be sitting there too. So at the instant the communication happens, you're both at that same point in the program, wherever those two pieces of the program line up. And when they're both there and ready, the value is transferred, and then both the sender and the receiver go on their way. Now, it is always synchronous and always unbuffered. It's easy to build buffered channels using mechanisms in the language, but the fundamental primitive is an unbuffered channel. Similarly, it's synchronous. You can simulate asynchrony. In practice, you rarely need it, but a lot of people seem to think it's important. So let me spend a couple of slides talking about asynchrony in this world. It's pretty easy to simulate an asynchronous send. All you have to do is launch a process to do the send for you, and it'll just complete when the value can actually be transmitted. And so you just launch it on its way. So to do that, you could write this. Let's say that you have a channel that you want to send on called ch and a value v. You can just write the prog that says accept a channel and an integer and send it, and then begin that in the background. So that will do the asynchronous send for you, because it'll do the send, and that guy will hang around until the send's actually done. But that's kind of clumsy. So we can do something which is a very common sort of pattern in Newsqueak programs to wrap it up a little bit. And what we do is we take this launching of the program and we bury it inside a function. And then the function itself actually does the send. So you call the function with send on my channel 23. I guess that should be a CH. But anyway, asynchronous send, this is this function, the channel and the value. And what the function does is it buries the begin of the process within. So you think of it as a channel, but you've now, essentially, this is isomorphic to an asynchronous send, but done as a function call. And so this notion of launching processes inside one-line lambdas is very, very common. And you'll see a few more of them. Now, asynchronous receive is, as you can guess, quite a bit trickier because you have to know when to receive. There's some signaling involved. It involves multiple channels and thinking about it. So I leave it as an exercise for the reader. But it's not very hard. The key point, though, is that the channel that you're using to communicate the return value back is also a way to signal that the value is ready. And that gives you a sort of handle on how to build these things. And you can use the same kind of observations to build locks and semaphores and all those lower level primitives if you want them that way. There's nothing wrong with doing that, but we're trying to avoid that in general. The key point is this one. When you want to discover when a process is done, that is, in effect, the join, you create the process with a channel that you will then read when you want to know that the job is done. And so you use channels as first-class values all the time to communicate states of things that are happening. So a few points about channels, because they really are important. They're used for communication, obviously. From the point of view of the language and the way it's used, as opposed to what is implemented, they should be used for all communication. You don't have to use channels for communication. You could use memory and whatever other mechanisms you want. But that's not the idea. The idea is you don't use shared memory. Instead, you use channels to pass things around, including arbitrarily large things. And the language tries to make that efficient. So you don't signal to say this data is ready. You just send the data. And it ties the signaling and the data together, which is actually an important idea that clarifies a lot of stuff. They're a lot like capabilities. Or if you prefer your Unix thinking, they're a lot like file descriptors. If I give you a channel, you have the ability to use it to communicate. If you don't have the channel, you can't. And so if I can use it as a way to hand off communication. I can also use it as a way to hand off sort of security aspects. If I trust this channel to be used right, I can give it to you and you can go with it. It has other interesting aspects like that are not there in the original CSP, which didn't have channels but only had processes. And of course, they're first-class values. You see a surprising amount of this kind of thing, where you pass channels around. If you've got a capability, the first thing you want to do with the capability is give it to somebody. What better way to give it to them than to send it over a channel? So you get these second-order capabilities, which are kind of fun to play with. I'm not going to use this stuff much, but I want to just mention it because it's important to the way some of the programs get written. Inside Newsqueak, there's an operator, or a control structure called select, which replaces switch, just in the way that become replaces return. You can use a select statement as a regular old switch statement, but it's more interesting when you have this kind of structure. What it does is, instead of having these just be values, these are actual potential communications that could happen. So you reach some point in the program where you're waiting for a bunch of stuff to happen. The way you ask, what should I do next, is you write a select statement that has a case for each of the possible communications that might proceed. And just to be perverse here, you'll notice there's actually some duplicate cases. That's perfectly OK. And what happens is you hit the select statement, and your program, your process, will block until one or more of the communications in the select statement is able to proceed. If one is available to proceed, then that will execute, and the program will do whatever that case statement says, and off you go. Now notice there has to be a communication written in here, and also, unlike a sort of C-style case statement, there's an assignment in here, because chances are if there's a receive, you want to know what the value was. And so you can grab it and print it out, or whatever else you want to do with it. You can also send a value here, and that also blocks. If there are multiple guys ready to go when the select statement begins execution, the system chooses one at random. So another way to think about this for you language mavens is that this is very similar to Dijkstra's guarded commands, right? But now with communication as the primitive. And again, this comes out of CSP, but it's fairly important. Yes?
When you say random, is that a strong random, or it's just up to the system?
No, it is a strong random, a random selection. There's actually there's a lot of randomness in the implementation of this system, which is in the implementation paper, which you can look up. And it is, there's totally non-deterministic. It's designed to be a non-deterministic select. In other words, you can't depend on the system properties to do something, favor one case over another. OK, there's a richer version of select. This is the same statement, but now these expressions are now more complicated. There's a thing which I don't know if I invented or not, but anyway, I hadn't seen it before, which is what I call an array select. And in these cases, the cases actually have an array value. See, I declared an array of channels up here. And then in the select statement, there's actually array expressions buried inside here. And these are all the same, really, but there are 4 versions because you can extract elements out. This says any element in the array can communicate. This says any element of the array can communicate, but tell me what the value I received was. This says any element can communicate, but I need to know which one did it. And this one is any value needs to communicate, but I know which one did it and tell me what the value was. So this thing inside the brackets here, this funny stubbed assignment, actually reports which index of the array transferred. So this obviously is there for writing muxes. And of course, a mux is a one-line select call. I mean, you wouldn't write a thing like this. You typically have one line just like that that does the muxing for you. And so you can have n-way muxing, and it's very, very simple. And you'll see in a minute why that comes up. So I think that pretty much covers the language. So let's actually look at a program in the language, because what's the point of having a program language if you can't write a program? This is a trivial program, but it's actually representative of the kinds of things you see going on. So here we have a prog called counter that receives a channel as a parameter, and then in a for loop, just prints out sequential integers to that channel. So prints out is the wrong word. It sends sequential integers to the channel. So to invoke it, we have to create a channel to use for the communication, and then we begin that prog with that channel as a parameter. So when that happens, the first thing the program's going to do is hit this send operator and block, because nobody's waiting for an answer. And so we actually execute. This is actually TypeScript. You can type this into the system, and it'll just run. You can type receive from C, and the system will print out 2. And the blue means that that's text that the system has printed out from running the program. You do it again, you get 3, and so on, and so on, and so on. So I've created this thing called C, which will just give me the integers starting from 2. Now, the reason I picked 2 is that 2 is a really good place to start when you're doing this next program, which is, I think, one of the most beautiful programs I've ever seen in any language, which is the prime sieve written in Newsqueak. I didn't know this program when I wrote Newsqueak, but the guy across the hall did. And it turns out Doug McElroy is credited with being the first person to write this, but Tom Cargill actually showed it to me. So the program actually ends here. This is actually running it. And it borrows counter from the previous slide. So the notion is the following. We want to write a prime sieve, which means we want to find all the primes that come out of this calculation. So we have this stream of all the integers going by. And what we want to do is filter out successively all of the numbers that are divisible by a given prime. Right? That's the definition of prime sieve. The way we do it is we create a process for each prime that filters out things that are 0 modulo that prime. And that process is called filter. So here's filter, which is a prog that takes a channel on which it receives the integers, a channel on which it sends the integers, and the prime it's going to be filtering out. And what it does is it just sits in an infinite loop, receives from the receive channel a value. If it's non-zero mod the prime, that is, it's not divisible by that prime, then we send it on. So it just filters, copies everything from receive to send, but throws on the floor everything that divides by the prime. OK? Now, that gets rid of one filter from the stream. The trick is, how do we stitch them all together? And I have a diagram. Let me go through the code, and then I'll show you the diagram, and we'll figure it out. So this is our actual sieve. And it starts, again, it's the same concept. You pass in a channel. This is the channel that's going to deliver the primes to us. And by construction, we have created the channel so 2 is the first one that comes along. And so the first number is always a prime. And so that is the invariant that we're going to run in the loop. We start the counter, and that means that the first one we know is prime by construction. That's 2. So then we go into a loop, receiving the value from the channel. By construction, at the beginning of time, 2 is the first one. Save it in P so we have it in our hand, and send it on to the prime channel, which is the output of this whole program. So that delivers the first prime to the caller of us. Then we make a new channel, because we're going to be stitching a bunch of filters together. So we make a new channel and start a filter process that copies from the channel we're currently holding onto into the new channel, and filtering out by the prime P, and then overwrite the channel so we're holding onto the output of it. So to look at it, looks like this. So this is the channel coming in from the counter, and think of this as being delivering all the integers down this way. So it delivers 2, 3, 4, 5, 6, 7, 8, and so on. We pick off the first one and say, oh, that's a prime. We print it out, and then we launch a filter for 2. And he's going to copy all these values, but he's going to filter them out so that only those that are non-zero mod 2 go through. The first one that pops out there is 3. We launch a filter for 3. He pops out a 5. We launch a filter for 5, and so on, and so on, and so on. And so this channel threading is essentially coming from the right-hand side, filtering new pieces on, taking this the output here, and making it the input to this guy, starting a new guy, stitching them on like pearls on a string. Hello? How do you go backward? There we go. So here's that sequence. Receive a prime, remember it, deliver it to our caller, make a new channel that we're going to use as our new receiver, start a filter copying the old receiver to this one, and remember the new receiver. So that's the whole program, plus the counter, which is the one-line thing from the previous page. And you run it like this. You make a new channel, which is our prime channel, begin the sieve. This is a very common pattern. You make a channel, create a process with that channel as its argument, let it run, read the data as you go. And then whenever you want the next prime, you just invoke this expression, and boom, it prints it out. Now, this looks very expensive if you think about all these processes and complexity and so on, but I'd like to make 2 points about that. Number one, computationally, from the complexity model, this is no more complicated than the regular algorithm. It's exactly the same idea. You just have to do all the divisions. This does all the divisions. That's all there is to it. And moreover, it's very hard to write a prime sieve that's any shorter than this. There are languages that are intrinsically more concise. Like you could probably write a nice one in Haskell. But the idea is that if you try to write this filter program, all the bookkeeping and the management of data and all that state is quite difficult. Here, it's all sort of hidden in the fact that you just start a process for every prime. So it's a strange little program, but it's actually quite pretty. And there's a lot of different ways you can adjust it to do it different ways. But this is probably the most concise way I have to write it. So people understand this example? All right. Try this one. I wrote this system to write Windows systems in, and the office next door was occupied by Doug McElroy, who's, as people in the room here who know him will attest, is fiendishly clever. And he realized that you could use this system to manipulate power series. So a power series is just an expression like this. It's the sequence of coefficients representing successive powers of a variable. And a common example is Taylor series. So here's the Taylor series for the exponential function. So you see it's just algebraically x to the n over n factorial, but you can also think of that as just 1 plus 1x plus 1/2 x squared plus 1/6 x cubed, and so on. And Doug said, let's represent, since we know that the x's are always there, let's just ignore them and think about the coefficients. So we're going to represent the coefficients of this power series, which is 1, 1, 1/2, 1/6, and so on, as a channel. And the idea is just like we use integers sequentially in the prime example, these are just coefficients identified by the sequence in which they arrive on that channel when you go and probe them. So here's our definition of power series, but we sort of weirdly invert it. Now, the way Doug did it to make it pretty was he defined a rational type. So these would be really rigorous mathematical power series. That's not very important. It just means the mathematics has to be a little functional rather than operational, but it's still pretty easy to define. So this type power series here is a channel of these rational numbers, which have a numerator and a denominator. And then there's a paper, which I'll cite in another slide or two, which you can read all about this, and I really recommend reading the paper. It's amazing. But for the point of this talk, assume we have ways of doing arithmetic on rationals, like maybe functions called ratadd, ratmul, ratdiv, that kind of thing. So if you have two power series f and g, and you want to sum them to make a new power series s, you could do it like this. You make a prog that takes a f and g that is going to sum, s, which is the return value, and you just loop doing receiving f and g's values, which are the leading terms of their series, and sending them onto the sum. So that sums two power series by taking the two streams, merging them into one, sending them out. It's almost like a geometric operation. It's very simple to do, right? But it's kind of clunky to have to functionalize it all like that. So the next step we do, which is really where things start to get interesting, is instead of having a function that takes the sum channel as an argument, we actually create it as a return value. And so again, it's this thing where you put the prog inside, the process inside the prog and invoke it. So we make a new channel, which is the sum we're going to send the values on, and then we launch a begin prog here that does that loop. Notice the invocation there. And then the return value for this function is the stream that we created that is the addition of those two power series. And this pattern is very common. I keep pounding on that. So there you go. There's a way that you can take two power series and turn them into another one by just calling PS add of f and g, and now you got a new power series in your hand. You can sum them. Now, summing is trivial, but in the paper, you'll see you want to do derivatives? Well, you drop the 0th term and then send forever ratmul of the next value times I, which is the index in the sequence. You want to integrate a power series. You emit a constant for the leading constant of integration, and then send forever divide the next value by the index. So there's integrate, and that's, I mean, you obviously need a little more boilerplate for that, but that really is integrate and differentiate power series. And the paper, Doug works out how to do multiply, divide, various splitting operators. It's really kind of amazing. And when he's done, he's able to do things like this. This is kind of a, don't worry about all the details here. It's kind of a lot of explanation I don't want to go into. But that expression from his little library will calculate the power series for the tangent function, which is notoriously difficult to express in computer code. And he got it down to a hell of an expression, but an expression nonetheless that's very concise. And the implementation of all of this is actually only a few hundred lines of code. That's the entire implementation of this thing in this language. And it's all made possible and concise by this stream notation that makes it easy to manipulate these variables as power series as actual values. I highly recommend reading this paper. I'll have a slide at the end with all the papers on it. It's one of the most amazing papers I've ever read. So what you saw in that last example, and to a lesser extent in the prime example, was this notion that you have a channel that represents some sort of contract. This contract is a sequence of primes or the addition of two power series. And it's important to think about that contract idea because that means it's really an interface. I mean, the entire interface to a power series in Doug's program is this channel. It's trivial, but it's also sufficiently powerful. You can express quite interesting programs with it. But of course, this is a real programming language. Let's build data structures out of this stuff, right? So what you can do is take a set of channels together that represent a more complicated interaction with a more complicated process. And that can become a much richer kind of interface, which I think is isomorphic but interestingly different from, say, an object-oriented interface to a class. So here you see this sort of sketchy version of it. You have some type called interface, which is just a structure with a couple of channels in it. I'm not saying what those channels do or what they mean, but here I've now got this interface, which is a set of channels that have some property that individually implement their contracts, but because they're channels to independently executing things, may actually execute independently and have other interesting properties. And I'll show you some examples that make this a lot clearer. And then to use such an interface, you make a type that holds these channels in it, and then you start that program which has some use of that variable in it and invoke it with that interface as a variable. So the instance of the interface is actually just the representation of the channel, and somewhat independently, there's a prog that uses that interface and operates on the channels that it embeds. And that's probably very confusing. So let's look at an example. This was the motivating example for Newsqueak in the first place. Actually, it's almost the motivating example for Squeak in the first place. But Newsqueak was the one where you could really write the program I wanted to write. So there's a paper, again, I'll cite the paper a little later, that goes into a lot more detail about this. I'm glossing over a tremendous amount of not only how it works, but also why it works really well, because I don't have a lot of time. But here's our idea. When you're looking at a program running in a Windows system or graphical environment, it's some box here, and it's got things it needs to talk to in the outside world in order to run. And I've represented them very schematically as the mouse, the keyboard, and the graphics model, right? And so we represent those as channels, and exactly what these mean, don't worry about for now. I don't have time to go into it, but the idea is there. So you have this type, which we call the environment for the client of the Windows system, and it consists of at least a channel for doing graphics on, a channel for getting mouse activity on, and a channel for reading keyboard characters on. And that's pretty much all you need to know. If you believe that this represents the environment, and modulo a few missing details, it is enough, then a client of this system is just a program that operates on that environment and implements the protocol that that interface requires. So you can actually define a type and then invoke things of that type with this model, and you have a graphics program. Well, that's itself not very far, but you can get pretty far by thinking about what you do then when you have a Windows system. All you have to do, if that model works, to build a Windows system is mux it. And so given this, OK, so here's a shell window that's inside this box doing God knows what. We don't care. All we know is that there's these three channels we use to interact with it, and it uses to interact with us. And there's arrows pointing different ways to stress the point that it can be a bidirectional kind of thing. Okay? And here's another client, which is an editor. And there's another one down here. And from this guy's point of view, he's just using this interface, and he's getting something that honors the protocol of graphics, keyboard, and mouse. And it just works. And he runs in all his sweetness and light. Okay? And this guy's got his own little world, and all he sees is keyboard, graphics, and mouse, and everything's wonderful. And then the Windows system itself, what it does, of course, is what's its world? Well, its worldview is it's running on a computer. It's got a keyboard, a graphics, and mouse operations. Looks exactly like an env. Guess what? It is the same exact interface. And so if you ignore what's to the right here, this isn't one of those client things. But it implements a mux to other ones. Depending on, for instance, where the mouse is on the screen, it might direct the events here, or here, or here. And the key point of this is that this interface is exactly this interface that it's muxing, which allows this to work. You can actually run the Windows system as a client of itself. And it's not that magic happens in order to make that happen. It's that the model makes it hard to make this not just work. It just falls right out of the design. And it's kind of a powerful concept, and very different from the way that event-oriented programming would think about doing this, right? This interface model with concurrent programming makes this thing actually not only easy to write, but the whole concept very simple to understand, and also very powerful. And there's all kinds of wonderful things you can do with it. Running the Windows system as a window is one. You can do things like, let's say that someone's left-handed, and they want to flip the mouse buttons over. You can just interpose a little process right there that inverts the mouse buttons. And neither side even knows about it. It's all transparent because the interface handles it. The whole program here, this thing, is less than 300 lines of Newsqueak. And in fact, the part that really matters, the non-boilerplate part, is a 60-line array select statement with some interesting operations in it. It's very, very simple code. It took me an evening to write. It took me 6 months to write the language and then an evening to write the program I wrote in it, which is not usually the order of doing these things. And this paper, which is almost 20 years old now, talks about this in a lot more detail. And if you're interested, I think it explains a lot of why it works well, and also explains many of the interesting examples that you can do with this system that aren't so obvious. One of the things I wanted to do and explored, but as I'll see in a minute, I moved on to other things, was the idea that you could take this Windows system and stick it here so that, for instance, a multi-window text editor could use the Windows system code as its own window manager internally. And that also falls out very naturally from the model. Now, this went on. It worked so well that I just said, this is great, let's just do it. And so having learned what we learned, when Plan 9 started, which was at roughly the same time, the Windows systems for that operating system were built in exactly the same way, but not in Newsqueak, but rather in a systems language for a lot of obvious reasons. And in fact, there are 3 Windows systems now that have been written this way that ran on Plan 9, 8.5 Rio and Acme. And it just worked great. And Rio, which is still a living program, still works. It's, I think, 3,000 or 4,000 lines of code, and that includes the terminal emulator. But it's a full muxed interacting thing that, by the way, also implements a file system, because that's the way Plan 9 is. But I don't believe it would have been possible to write that program if I hadn't gone through the whole Newsqueak thinking about concurrency model. The program was just a lot easier to write because of that. So there's a couple of papers that talk about this. This 8.5 talks about the Windows system that was first written for Plan 9 that looks like this. The second one, Acme, is a little bit richer system. It's still a Windows system, but it does a lot of other things. But it's interesting because it has, I think, a particularly clear section in it about how the system model applies to building this kind of Windows system. And in fact, in the end, essentially all the major Plan 9 services, user-level services, ended up being written with this kind of approach, which I'm now going to talk about in more detail. So what is the system model here? I mean, I said we're going to build systems this way. What does that mean? Well, first of all, what you want to do is define your components as interfaces that capture the communication that to a thing that's going to do whatever it is it's going to do. It's going to interact with a client. It's going to interact with a back-end server, whatever it's going to do. And all of the data flow and communication that's needed to manage that thing is done with communication over channels. Now, it doesn't need to be shared memory. It doesn't have to not be shared memory. But the notion is there's an interface with communication and channels that exchange stuff. The interface itself is a type that has in it all of the elements of that communication stuff. And you can implement various versions of that interface just by writing anything that operates on that type, because the type is just a channel. It's not an interface in the object-oriented sense. It's just a set of channels. And anything that honors the protocol for those channels will implement that interface. So it's very easy to do. So in the Windows system example, the shell, the editor, the Windows system itself, those are all implementations of that interface. And then where it starts to really matter is that the composition of things, when you start building systems that connect together lots of components like this, the composition of their execution tends to be linear in the complexity of the design. Adding another thing just incrementally increases the complexity. But you get this superlinear expressibility. You can start to do much more complicated interactions, like I mentioned, where the Windows system and the editor and the Windows system are all interacting in interesting ways. And it's worth thinking a bit about how that compares to state machines, which is almost exactly the opposite. In state machines, you have exponentially difficult complexity trying to write the composition, but when you're done, you get this really piddly, inexpressive result. And this model, I think, is a real counterpoint to the way people think about state machine and building things as state machines. And also, when you actually do this, the interleaving of execution falls out for free, which is a really powerful idea when you're starting to think about systems and large-scale performance and hundreds of clients talking to you and that kind of thing. You don't have to worry about bookkeeping. It's all taken care of by the model. So as a sort of bullet item to think about, think of this as composing the interfaces themselves, not the state machines. And I'd like to stress that the point of all this is not that it's parallel. I don't really, for the point of view of this side of things, don't care that it's parallel, but it's nice that the parallelism falls out. If you build systems like this, they will run in parallel well. You won't have issues with locking and things that tend to bedevil stuff that works at a lower level. The same is almost true for things like networking and remote execution. It doesn't fall out quite so neatly, but it's easy to imagine if you have an interface that's defined as a channel, how to turn that into something that works across a network. It's not, you have to think about it a little bit, but it's a lot easier than thinking about how you do shared memory across a network, for instance. So let me leave you with this kind of thing. In putting this talk together in the last few days, I realized that I should probably resurrect Newsqueak and try to write a web server in it, because I think it's a pretty nice idea for how to do this. And it's a very similar diagram to the Windows system diagram, right? Here you've got these client stubs, this is your program. This is the web server. And he's got a little stub process that's interacting, dealing with the HTTP stuff coming from the browser and doing various I/O to the web server, which is muxing all these clients together. These things are really cheap, so we can have hundreds or thousands of them. Lots of browsers all interacting independently. It's all taken care of. But on the flip side, the Windows system touches this a little bit in things I didn't go into, but you can imagine the backends for the web server, implementing various services that the web server is providing. The same kind of model would work over this side too. And so this whole thing can become a composition of interfaces. And when I think about doing that versus doing state machines, there's some very interesting possibilities for how it works. And in fact, there was a Plan 9 web server that you could probably draw this diagram for, but I didn't write it, but I'm sure if you squinted a bit, this is what you would see. So in conclusion, I'm sort of presenting this model, which has been around for a long time, but I think has been forgotten by a lot of people. I still miss it and been thinking about maybe resurrecting some of its ideas again. The thing is that when you have message passing and concurrent processes, you have this very powerful model for thinking about programming that doesn't really have anything to do with parallelism per se. There's nothing parallel in the Power Series example. And yet the expressibility of the model for writing that program was really powerful. Sometimes, though, the problem you're working on is intrinsically parallel, like you're building a server, and then it's obvious that you get benefits. But there's benefits even when it's not. You need both concurrency and communication. This is sort of my criticism of the low-level semaphore lock kind of thinking, where you think a lot about the locking and control, but you don't bind that to any kind of data model. And you really want to have a higher level thing that unifies communication as a synchronization plus a data transfer, because then you can really think about data flow as a way of internally doing things. And the fact that the notation is fairly concise is important. You can obviously do this as the functional notation or just function call notation with send and receive and stuff. And in fact, that's how we did it in Plan 9 in sieve programs. But you want to have the thinking in your head to make it very easy to write these things down so you understand it. And if you get your head around this stuff, you find that it really clarifies how you think about interfaces and sharing and communication and composing systems. And it's a very powerful model that's quite different from the way most systems get built nowadays. So I'll just leave this slide up to finish. These papers are all online. There's the original Squeak paper, which is weird. You probably don't want to read that one. This is the Newsqueak document, which is quite short and easy to understand. This is Doug's amazing paper on Power Series. This is sort of the Windows system paper, which is actually written before the Plan 9 Windows system. It's just about the Newsqueak Windows system and how I got there and how it works. And there's a lot more talk in there about what it really means. The Acme paper has probably not interesting to most of you, except this one page in there about how the system model is used to mux together this composition of services, actually very much like that diagram, is kind of interesting. And actually, I resurrected the binary. So in my bin directory on the NetApp, there's a Squeak interpreter called Squint. The code is from 1988. A lot of the libraries for graphics and so on just aren't there because I couldn't resurrect them. But all the examples I've shown you today have been tested inside this thing. And the Power Series example and others are available under this directory to play with if you're interested. So we have a few minutes left for questions, I guess. Matt?
It would be very easy to implement panels on top of things like mutexes in a language like C++ or Java. Is there a reason we are not doing that more?
I think it's a very, yes, I understand. I think it's a really good idea to think about implementing this kind of communication channel model on top of mutexes in C++, and I'm certainly thinking about why that isn't there and maybe trying to fix it. A lot. I'm thinking about it a lot. John?
So, when I would use a callback in current Google code, I use a channel in your code to get the answer back, plus more places. But so what's the relative cost of a channel versus a callback?
The question is, what's the relevant cost of a channel versus a callback? And I think if you were doing reasonable implementation of channels, they'd be modestly more expensive, but not punitively so. The payback in terms of the complexity of the program itself and the bookkeeping it needs to do in order to manage its callbacks might more than offset the extra complexity of the channel itself. If you're just using a channel for signaling, it's very cheap. It's just a lock and a data transfer, which is typically just an integer or something, or a pointer. And so it can be very, very cheap. It depends a lot on what the callback's doing and how you compare specifically. But intrinsically, I don't think it's significantly more expensive. And the simplification, how you use it, may mean that your whole overall program becomes actually more efficient. But obviously, that depends very much on the details. Jeremy, do you have a question? The question is basically what's the implementation overhead for all this communication stuff, and in Newsqueak itself, where I wasn't really too worried about parallelism, it was all in one process. It was fairly simple implementation. There is an implementation paper which I didn't list here, but you can find it, that talks about what the algorithm is. For LF, which was truly parallel and worked on a shared memory machine, Phil spent a lot of time tuning the algorithms to give the same semantics but with efficient communication. And there's a lot of optimization you can make when you're in a language like this to recognize simple cases. And the trick for making this work well is often to have the compiler generate different code for different forms of select, where you can actually generate more compact, less locky setups for some of them. In the most general case, it can be quite expensive, obviously, but you work hard to make sure that you don't have to pull the channels and things like that, and construct data structures that will suitably manage the arrival of data so that things stay expensive in the amount of communication going on rather than the number of channels involved in the operation, which can be quite a bit, well, almost always be very much smaller. But yes, there's a lot of stuff about how to do that, and obviously we've thought about that a lot.
There have been
Right. Yes, there are CSP-like libraries for a lot of languages. There's something about having the notation there, and the select operator is hard to do as a library and things like that. Yes. Mm-hmm.
How do you debug your program?
How do I debug my programs? I knew that was going to come up. That's why I put a slide after my final one. Everyone obsesses about debugging concurrent programs like it's some sort of plague. And you know what? Deadlock's just a bug. You fix it, right? And moreover, when your program does deadlock, you run the debugger. You look at the stack traces of all the processes. You can see what's going on, and it's just like any other bug. How did I get here? What happened? What do I fix it? But there's actually, that's pretty glib, but I think there's a lot of truth to it. But there's more to it, which is really important and important to understand about deadlock. One is, unlike almost any other kind of bug I can think of, there are amazingly good tools for preemptively discovering deadlock in your program. There's things like a program called Trace. There's Gerard Holtzman's program, whose name eludes me for a moment. There's others where you can represent the program model to this tool, and the tool will tell you you're going to deadlock if you do this. So you can actually automatically find programs bugs in your program. And in fact, Gerard's stuff more recently, he extended it so that he could actually look at our C programs that use this model, the kernel source in some cases, and identify deadlocks or, more importantly, lack thereof in certain of our more difficult algorithms. So having automatic tools to solve it is an interesting thing. And the final thing, which is experimental, I never actually did it, but I thought about it quite a bit, is when you have an interface that's so cleanly defined like this, and you're doing something like the Windows system where you're going to plug in a new client, you might not trust the client. If you're going to get a deadlock, it's probably because that client is misbehaving. But you could imagine, because the interface is so well defined, sliding a little shim interface in here that guarantees that this side is deadlock free, even if this one screws up. And not only report when there's a deadlock and isolate the rest of the system from the problem, but kill this thing off if it's aberrant. And I think, I've never done it, it's hypothetical, but I think between the point of having the ability to identify them before they happen and the ability to perhaps even solve them dynamically, there's a really interesting power of things that's often forgotten. But fundamentally, they're just bugs. You look at the stack trace, you see how you got there, and you fix it. I think we're almost out of time here, by the way.
By default, everything is synchronous, and you can simulate asynchronous style. But even if you go into asynchronous style, you can still apply the same principle.
Oh, asynchrony doesn't avoid deadlock. No. Asynchrony means you don't wait. It doesn't mean you don't have bugs. So I think if there's a 2 o'clock talk, we probably need to stop now. All right. Well, I'll put this back up.